Hi, this is Craig coming to you almost live from San Diego. It is May 18th, 2017, and this is a talk that I gave earlier today at SMST in the afternoon, one of the computational simulation and testing sessions, of which there are many, and there have been lots of great talks. So I did try to record this during the session. I failed to do so by failing to click a button. So I'm going to just briefly walk through the slides, and for those that might have missed the talk today here at SMST, just kind of walk you through some of the things that you will be able to learn more about online at a website that you probably already know about, because that's probably where you found this. So let's get started. I'm going to skip the outline, just jump right into the motivation. So the crux of my talk sort of gets at this idea that we talk a lot about inclusions in material. It's been a big topic of conversation at the conference. It has been for many years. A lot of effort in the industry to make ever more pure materials because we know that material with fewer impurities, oxides, carbides, voids, etc., has better fatigue performance. Not a big surprise, and something that has been subject to a lot of interest and effort for a long time by many in this industry. On the other side, we know that our devices have a certain geometry and are subjected to certain loading conditions, and therefore have certain hotspots that are a function of those geometries and loading conditions that are distributed in space, that have some volume and have some orientation and have some spatial sort of component to them. So both on the material side, we have inclusions that have some spatial distribution. On the device side, we have sensitive regions or hotspots that have some volumetric distribution and density. And the idea here is that somehow the intersection of these two volumetric distributions has something to do with the probability of failure and the scatter that we often see and are frustrated by in our fatigue testing. And there's been a lot of work on both sides of this Venn diagram, but there have not really been great methods to try to tie these two things together and to say something about the risk that's related to what is essentially the sort of probabilistic overlap of a hotspot ending up at an unfortunate location where there happens to be one of these inclusions. So the hypothesis is that we can do a better job of predicting durability by developing some methods that will allow us to bring these two things together. And in order to do that, we had to create a bunch of new tools. And as you probably already know, these tools are all online. So that's a kind of an experiment, something new that we're trying here related to this talk. And all the raw material, source code, source data, design files, simulation inputs and outputs, and all that kind of good stuff are all available online at a link you'll see at the end if you don't know about it already. So what we have created to use as an example for this talk is a generic geometry component. Okay, and all of the again, all the design files and simulation files to create, expand, crimp, and deploy and fatigue this particular component are all available online. So you can go check all that stuff out. And this is a Nitinol component that is sort of representative of things that are realistic, but it's deliberately generic. It's non-proprietary, something we can use in talks like this to, as an example. So here we can see one of the animations that did not play when I actually gave this talk earlier today. Good for you that you're seeing it here. This basically shows the fatigue condition that we imposed on this generic sort of toy geometry, and it's just a 9% change in diameter that we're imposing, and we do that because it creates results that that are kind of interesting. So here we see the output of a typical fatigue simulation, which we will often express in terms of mean strain and strain amplitude. So each of the points in what we describe as a point cloud here relate to one of the elements in that finite element model. And typically we look at a plot like this and say that the point that is closest to the top is the most critical point. We look where that is, and if it exceeds a certain threshold, and use that to determine risk. And that I have always found frustrating because we look at a single point, whether it's above some quasi-arbitrary line, and we decide if a device is good or bad on the basis of that, kind of a binary decision. Not really a great way to assess risk in a quantitative way. Very difficult to create safety factors that are actually meaningful with this approach, but it's kind of the state of the art. It's where we are as an industry. So the point of this work is to try to get beyond that and to find some new ways to assess risk. So when we actually sort of consider that we will generally judge the strain amplitudes above a certain threshold to be critical, we'll draw that threshold somewhere, and it may vary as a function of mean strain, as we've heard at several of the talks today. But let's say that there's an arbitrary threshold at 0.4% strain amplitude. So if we look at all the points in our geometry here that exceed that threshold, they're highlighted in this chart that we're looking at. And you'll see that there's a bunch of little specks. There is relatively very little of that volume that is actually at risk, that is actually experiencing strain amplitude exceeding, in this case, 0.4%. So the crux of the idea here is that those points that are highlighted in this chart are the ones that are at risk. So the unfortunate circumstance of a inclusion or a large inclusion ending up at one of those points that are highlighted is what's going to result likely in a fatigue failure. And that's what we're going to try to explore in this talk. So in order to do that, we need to add some tools to our toolbox to be able to extend the output that we get from finite element analysis that we commonly do in industry. So most of the times that we do simulation, we generate lots of information and kind of throw most of it away. We will usually look at mean strain and strain amplitude on the basis of some maximum principal strain that we're extracting from the model. And we generate lots of information and can generate lots of information that we kind of ignore. So one of the tools that we've created here is a Python script that interrogates an Abacus output deck and extracts lots of information. So you can see what they are. They're listed there. Most notable on this list is integration point volume, because we want to try to get at some volumetric measures that hopefully are going to give us some more insight about the models that we are assessing. So we get things like integration point volume, hydrostatic pressure, volume fraction of martensite, all of these other things. Go check out the script, and you'll see everything that we do. So from this script, we can now create the point cloud that we saw before. In this case, we've done some filtering on the typical point cloud. We've filtered out the points that are in compression. We usually don't care about those because it is generally understood that tensile forces are required to propagate cracks. So cyclic strains that are compressive in nature are going to be less of a risk than cyclic strains that are tensile. So the ones that are in red there, we've set to 0. Those were compressive by our hydrostatic filter that we pulled out. So that's a typical point cloud. And now since we have all this other information, we can express our fatigue criteria in different ways. In this way, we're showing a Smith-Watson-Topper, or SWT, point cloud. This was discussed earlier in the conference today, and I believe yesterday, as one of the fatigue criteria that perhaps is more predictive or more insightful. So again, once we have a script that we can use to suck all this information out, it's pretty easy to reassemble it in any sort of manner that we like. And this one, in fact, may be quite useful. We'll see. So another really interesting thing that kind of goes to a little bit of an aside, but I think a really interesting aside that is enabled by this kind of approach, is that we can actually look at the phase state of each element in the model. And there's been a lot of talk at the conference and and around about this notion, which has been around for a long time, that fatigue durability, fatigue performance is in many ways expected to be related to the phase change from austenite to martensite and back again. It's been described as a front of transformation moving through the material. And with these methods, we can look at the state of each element at each cycle of that fatigue cycle that we're interested in, understand if each point is austenite or is martensite, and then we can compare the loaded and unloaded end of that cycle, compare each point, and figure out which points are changing phase. And if you're interested in how that happens, you're going to have to dig deeper. I didn't get into it today, but I did suggest that folks look a little bit deeper, because we do have to do some kind of weird things to get this. It doesn't naturally fall out of the model, but there's some kind of clever, maybe clever or maybe stupid approaches that we've used to do this. But it's interesting, because if in fact these points that are flipping from austenite to martensite and back again at each point in the cycle, if they are the culprits, they are all over the place. They're at a whole range of mean strains, at a whole range of strain amplitudes. Normally, we're looking at the upper right of a plot like this, and we say those are the bad actors. Those are the ones that are going to initiate fatigue. But if, in fact, these points that are flipping from A to M and back again are the culprits or are part of the culprit, they may be different points than we're used to looking at. So it's interesting, and I think worth some more study. So again, the point of what I'm talking about here today is to put these sorts of results in volumetric terms, which is something that we've generally ignored, I think, as industry. So that plot that we just looked at, we can express in terms of a volume histogram. So if I flip back for a minute, you know that each one of these points relates to an element, an integration point in the model. But you don't have any idea looking at this about how much volume is associated with each one of those points. You get some indication that the points at the lower left are overlapping each other, and in fact most of the volume of the model is down here at the lower left, because we see lots of overlapping points. But if we take that same data and express it in a volume histogram as we're showing here, we can see an idea of how much material is, for example, exceeding a strain amplitude of 0.4% or 0.6% or whatever. We can look at that to the right of any of those points, and the way that we've expressed it here, we've actually colored the regions red, green, or blue to indicate the volume of material that is austenite, that's flip-flopping back and forth, and that is martensite. Now, what to make of this, how to think about it, is definitely going to need some more thought and study. But again, the tools that we're talking about here today give us the ability to actually explore those questions, which is pretty cool. Okay, so now we've got the FEA toolbox that we need, and we're going to need to move on to looking at the material itself with some novel methods. So we're going to talk about sub-micron X-ray computed tomography, which has been a lot of fun for us to explore. So what we're looking at here is the typical way that we usually look at inclusions in material, which is standard metallographic techniques. We take a sample, we cross-section it, we polish it, and we look at it with either light microscopy or backscatter scanning electron microscopy, as is the case here. And we find some way to get a contrast between the inclusions and voids and the matrix material, and we can then sort of count up the dark spots and use that to somehow assess how much non-metallic inclusions or voids there are in the matrix. Generally as an area percentage. And that definitely gives us a lot of insight, but the methods to do this are not always straightforward or perfectly clear. A lot of discussion in the ASTM meeting here on site yesterday, debating different methods and possible ways to standardize this. Everyone has their own approach. Generally, this is good information, but it doesn't really give us what we need because this is two-dimensional information. We're looking at slices here, and we're not getting a three-dimensional picture. So you can make some assumptions and make some guesses about how to translate that two-dimensional information into volumetric information, and this is something that we talked about a few years ago at SMST, and created a graph that this was shown in 2013 that gives you some idea of the probability of inclusions larger than a certain size for different grades of material. The orange line being VAR material, or kind of a typical SE508 type of material. The green line being high purity VAR material, or what we would call SE508 Eli material, and that's what we refer to. And there are some results here for some other materials as well. The general trend being that higher purity materials give you a lower probability of inclusions larger than a given size. Not a surprise, but in order to get to this point, we had to make some kind of crazy assumptions that we wanted to try to get past for this work. We know that it's a good idea to do all this stuff because of the work that's been reported by Scott Robertson and others, and has also been mentioned at the conference here this week, where we know that in improving the purity of material gives you better fatigue outcomes, lower probabilities of fracture, pretty well established and well reproduced. So we know that there is definitely a benefit. So let's see if we can dig deeper. So what we did here is we created some test specimens. You can see the material that we used, 8x7 superelastic tubing. We had it in a few different flavors. And we created a laser cut pattern that you see on the right there, which is basically a bunch of these little matchstick samples that are about 0.5 millimeter by 0.5 millimeter by about 50 millimeters. And we took those samples and put them into an NArea Zeiss Versa 520 micro CT scanner over at Stanford. And when you do that, we didn't know what we were going to get, but we were pretty happy when we saw the first set of results. So basically you get a stack of images out of this thing. In this particular case, we get about 2,000 images. They're a 16-bit grayscale image, and when you do a little bit of thresholding and window leveling, etc., you can get something like what you see at the right, which is an indication. You're looking at the cross section there of this strut, and the dark spots that you see are inclusions and or voids. So we're definitely getting the contrast that we need to see the difference between matrix and inclusion. And what you're seeing on the right there is basically 50 or so of these 2,000 slices. We're just kind of indexing back and forth through them. So we know that we can see what we need to see. So that was pretty cool. The next step that we needed to do, though, was to figure out how to systematically look at all 2,000 of those slices for 3 different data sets. And that turned out to be quite a challenge. I'm not going to get too much into how we resolved that, but if you want to learn more about it, there's lots of information on the website about the methods that we used to do that. Basically, this was an exploration in machine learning using open source tools. There was a lot of I had to do a lot of learning to figure out how to even implement a lot of this stuff, but it was a lot of fun and very computationally intensive. So basically what we do here is train this model. What does error look like? What does matrix look like? What does an inclusion look like? And then kind of repeat that training a few times until the algorithms get it right, and then deploy those algorithms on each of the data sets. And what the algorithm will do is to come back and classify each pixel or each voxel of each of these data sets with a probability that it belongs to the classification of either matrix, non-metallic inclusion, error, or edge. And then basically we've got a sort of a probability map of the entire sample set, which is pretty neat. So what can you do with that? You can look at that probability map, and in this case what we've done is created what's called a maximum intensity projection, which looks at the entire volume and projects it to a plane. So at the left you're seeing what is effectively a transverse plane, but it's like I don't know, 2,000 transverse planes superimposed on top of each other. So you're seeing all of the inclusions through about 1 millimeter of thickness on the left there. And on the right, you see all of the inclusions through about 0.5 millimeter. That's just the same sample rotated 90 degrees. So on the right, you can see the orientation of what we call stringers, which are these kind of broken out and elongated bits of void and inclusion. One of the interesting observations here, which was part of what motivated this whole study in the first place, was a question about, hey, are inclusions more prevalent at the ID or the OD, or is there no relation? And what we found when we looked at this is that it does seem like inclusions have a higher density closer to the inner diameter of the tube, and presumably the center of the ingot. We really interested to take these methods and use them on wire and other material and see if this this in fact holds across across different material samples. But from what we see here, it seems like there is there is an indication that there may be a trend. So what you're looking at in this picture is standard material, what's been referred to as Generation 1 material, SE508, kind of the backbone of the industry for many, many years, from which probably most devices that are out there have been made. So it's kind of there's a lot of spots there, but it turns out this material actually works incredibly well and has done a lot of great things in the world. So what I'm going to show you next is going to be quite a bit different. So the next slide is going to be SE508 Eli, what's called Generation 2 material. And the next slide, which I'm not showing you yet because there's a little bit of drama here, was created using exactly the same methods, the same techniques, the same algorithms, the same absolutely everything. And the picture looks dramatically different. So it was kind of shocking. We did 2 of these. After we saw the first scan, we did a second scan. They basically both looked the same, almost completely absent of these large inclusions that we see in SE508 standard material. So quite a shocking difference in purity, cleanliness, however you want to put it. My guess is that this is a little bit luck of the draw. If we were to scan enough more of these things, we would see some stringers and we'd see some larger inclusions. We know that they're there because we've seen them with traditional methods, but it is a dramatic difference between the 2 types of material. So now that we've got this probability map, we can actually isolate the inclusions themselves, and they are, again, inclusions and voids. I'm not trying to distinguish between them, but we can measure their volume. We can locate them in space and kind of understand their geometric distribution and density. So we're back to the SE508 now again, and what you're seeing was not seen in the actual conference today because the animations didn't work for some reason. But what you're seeing is that sample rotated around in space. The colors map to the volume of those inclusions, and you see the pink one that's floating around there. You see the volume in terms of cubic microns is what the scale is there. So quite a pretty animation. When we look at the same thing for SE508 Eli, there is much less to see. So there's just not as many stars in the solar system, but you get the idea. So now that we've got all of that, we can look at kind of translating all of that graphical information into some sort of numerical form. So what we're looking at here are histograms that map on the left inclusion count by size in cubic microns, and on the right inclusion volume by size. And the general idea, these are log scales, by the way. The general idea is the top ones there in red are SE508 Eli. There are a lot more inclusions, and there's a lot of big inclusions, right? And the big inclusions, kind of are overweighted in terms of, on the right when we look at them by size. Whereas the 2 Eli scans definitely have a different signature to them. There are fewer inclusions, and they tend to be smaller, and we can see that in those histograms. So kind of to distill this down a little bit further, we need to introduce some statistics into the mix. And folks at SAYS had a great paper in the SMST journal a couple years ago that looked at inclusions in a variety of different Nitinol materials and found that they tend to follow an extreme value distribution in terms of their size. So this is a statistical thing, and within the realm of the extreme value distribution, there's a particular formulation called the Gumbel distribution, and they found that inclusions in typical material follows an extreme value distribution, Gumbel distribution. I kind of used the methods that they suggested and found that, in fact, the inclusion sizes that we found in the scan also seem to follow that extreme value Gumbel distribution. So we fit all of our data according to those statistics, and we did that in all 3 directions, right? Because we have a volumetric data set here, so we can consider the projected area or the projected size of these inclusions in the transverse direction and then in 2 different longitudinal planes. And we express things here in terms of a Gumbel parameter. we've done this fit, and in terms of density. So the Gumbel fit requires a location parameter mu and a scaling parameter sigma. So we did that for SE508 and for Eli, and we've basically kind of got the whole thing now down to its sort of essential fingerprint for each of these. It's kind of a mathematical signature, again, for how to characterize these. I didn't mention in the talk this afternoon, but I'll mention here that we did assume a cutoff of 8 cubic microns. So in other words, volume inclusions of a volume of less than 8 cubic microns were not included. They were basically filtered out. And that's because there is an outstanding question about at what point where's the meaningful resolution limit? We felt pretty comfortable with 8 cubic microns. The scan itself had a resolution of a half a micron. So if the 8 cubic micron was in fact a cube, that would be 2 microns by 2 microns by 2 microns. So there's quite a few voxels there. Of course, the inclusions that we're looking at are generally not cubes. They tend to be elongated. So, there's a little bit of differences there, but we felt pretty comfortable with a cutoff at 8. I do believe that we could probably push that cutoff lower. It's going to need a little bit more work to sort that out. So now we've got a mathematical fingerprint or signature for each of these materials. So let's hold on to that and let's go to the casino. So Monte Carlo risk assessment is a method where you basically sort of randomize variables to try to match outcomes that have some random or probabilistic nature in real life. So in this particular case, what we are randomizing is the size of location, the size of inclusions, according to the parameters in the table that we saw a couple of slides ago. There's that location parameter and scaling parameter. If I feed that into this quantile function for the Gumbel distribution, basically I plug in a random value between 0 and 1, which I can generate in a script or whatever. And when I plug some random value between 0 and 1 into this equation, I get back a distribution that follows the extreme value Gumbel distribution for size of inclusion. So basically that's what we're doing in the script. This is what is being randomized. Tom asked how one of these dice has 9 pips on it. I can't explain that, but I did find it on the internet, so who knows? It must be true. So I created from this, I had to make up a term. I call it a fortune cloud because it has something to do with how lucky you are or are not. So if you think about what we are looking at when we randomize the size of our defect, which is expressed here on the x-axis of these charts in terms of root area, it's kind of a defect length measurement. So the x-axis is representing the size of a defect or inclusion, if you will. The y-axis is representing the stress, the cyclic stress that we're getting out of our finite element analysis model. So when we thought about that Venn diagram where we have hotspots are on the y-axis, the vertical axis there, and we have inclusions are on the horizontal x-axis. The question is, how often do we have a large inclusion happening to find itself at the location of high stress? So that would be the upper right-hand corner of one of these plots. So the question is, how often do you have a point in the upper right-hand corner? We see a few of them. This is looking at one of the Monte Carlo cases. It's just a single run. But you can get an idea that it's pretty rare that you get something in the upper right, that you're very unlucky. But it does happen. Okay, so that's what one run looks like. Now, what do we do with that information? Well, we can take information about stress and information about defect size and plug it into a formula that looks like what you see here and calculate something called K, or stress intensity factor. And if we can calculate a stress intensity factor, we can calculate a change in stress intensity factor, delta K. And that has something to do with crack propagation in linear elastic fracture mechanics. So this is a K, or delta K, model that was proposed by Murakami in the 80s and was referenced by Urbano and colleagues in that SMST paper from a couple of years ago as a way to estimate, again, the stress intensity factor K as a function of stress and area, which is something like an indicator or predictor of of failures. That's what we're looking at here. So of course we can do that now for each of the three directions. We can calculate a k in the x and the y and the z. And for example, k in the x direction is a function of the defect area in the yz plane, and then the complement is true for y and z. So we can go ahead and calculate all of those things. And when we do, for a single run, again, we get a point cloud that we can express this way in terms of delta k on the y-axis versus k on the x-axis. And generally, we look at this and say that higher points are at higher risk. And in fact, on the left, the blue-green there, we see that for the Eli material, we are seeing, in this particular case, a delta K that gets up into the 1.25 range. And for the Eli material, we're seeing a delta K that's closer to 0.5 or so. That is, again, one roll of the dice. Okay, so when we roll the dice lots of times here, which we're about to do, 500 for each of the material conditions, we're going to record the maximum point that we see in each of those cases, so the point that's circled there. Okay, and that's what we're going to represent on the next chart. So this chart shows the result of 500 runs for Eli, 500 runs for SE508. And you get a sense here for the fact that, again, the SE508 gives you higher delta Ks. That's not a surprise because the defects are larger. And you also get a sense here that the Z direction is the most critical direction for this particular loading case. And that's actually kind of fortunate because Z is the axial direction or longitudinal direction. And if you think about the area of defects in the transverse plane, that's where the smallest projected area is, right? Our defects tend to be elongated with the texture of the tube. So this is kind of a lucky circumstance for this particular case. And again, this is just one case. I don't know how general it is, but in this case, going forward, we're just going to focus on the Z component of delta K. It's a little bit easier to look at. So now we're going to look at a version of this fortune plot, if you will, for 500 plus 500 runs. So again, each one of these dots on the plot here represents one of 500 cases for the Eli material, the SE508 material, and once again, points toward the upper right of those clusters represent the sort of worst possible case combination of large defect and high stress. So something about the density of these points toward the upper right gives you some kind of a way to quantify how likely it is that kind of unfortunate combination is going to happen. All right, so we can now take that information and put it into a histogram, and that kind of boils things down. So we're looking at the maximum delta K now for Eli and SE508 in each of the three directions. And not surprisingly, again, for each of these cases, our delta K for Eli is significantly less than it is for SE508. So that's the kind of thing that we can do with this sort of information. There's lots of limitations. I did not talk through them all in the talk today because we just did not have time. Again, I'll let you read them. You can download the PDF. I wanted to make sure there's a record of them here. There's probably lots more limitations that I didn't think of. But the point of putting all this information out there, again, it's new. Maybe it's a little bit crazy, but a lot of smart people in the room today, and I'm sure they're listening to this. So critical review and feedback, greatly appreciated. Please do comment back and let us know how you think maybe we've done this wrong or perhaps how it could be better. And do encourage you to download all this stuff and see if you can find some use for it yourself. So to that end, there are lots of resources online, some, 80 megabytes or something, probably actually a lot more if you include the ODBs and so on. They are all on GitHub, which is the nerdiest possible way to share all of this stuff, which is why I think it's kind of fun. So this information is both in words and in code. You can consume it in one way or both, or however you like, and we hope that you will do so. As you probably know, you can find all this stuff on GitHub or just follow this short link. So thanks again, and we really would appreciate your feedback and to hear what your thoughts on how all this stuff comes together and how, again, we might be able to make it better. So thanks.